Testing, 1, 2, testing. Looks like everything is working just fine. Okay, let me go ahead and minimize this out. And now that we have all that set up, I can go ahead and turn this on. Okay, there we go. That works. Everything there looks fine. You should be able to hear me fine. Go ahead and start. Let's see here. So, sure, why not? So, let's go ahead and start start my channel spamming, basically. So, why is that in caps? Okay, that's fine. Not a big deal. Let me. Okay, here we go. And then I'm gonna put also this in. Let's see here, more 16. Community events. We'll do it here. More 16. Reverse engineering. Sorry. First couple minutes is always me going, I'm putting everything in here, so, you know. That works. Okay, that's all where well, I guess here is fine. And try my hand at some rudimentary PG-16 reverse engineering. Should be fun. So many Discord servers that are ROM corruption, game hacking related that I'm a part of. So, let's see here. So, I'll get started here shortly. So, okay, all right, that should be everything that I feel warrants. I guess not. One more. There we go. Most servers that I'm in. All right. Anyway, so I think what we're going to start off with is essentially we're going to start off with how this is normally done. So this is usually done with usually Nintendo games. So what you would do is you would open an NES ROM, and this is what's called tile viewer. And we'll take one that's notorious for using character ROM, so no compression or anything like that. So we'll take something like I don't know, something that I know is character ROM, Kirby's Adventure. Okay, so what we're looking at here is Nintendo games. Nintendo ROMs are organized with program ROM first, then character ROM, if any. So here, I mean, this here is like the let me make sure that you guys can see that. Yeah. So this here is that little thing here is that's like the header. Don't worry about that. You could just hit right once to change the offset like that. So looks like I've got the add to Spartan first. Yes, you are first. Have a cookie. All right. So all this, that's your code. That's your data, music data, level data, so on and so forth. Kirby's Adventure is a big game. I don't know why I chose this, but whatever. I should have just chose Super Mario Brothers if I was being smart. So, everything is blah, 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 blah. So, in a Nintendo game that has a character ROM, you go down far enough, what happens is someone gets your Patreon account. Like if someone joins my page, depends. So, I'll go over that like really quick since you asked, and you asked nicely. So the $1, very basic stuff. Just you get to see the list of games that I'm working on. You get access to the special Patreon channel that no one really uses on my Discord. Um, just basics, exclusive videos that I might want to put for patrons, which I kind of stopped doing because I only have 5 patrons, and it was kind of hard for me to justify exclusive content for 5 people. I don't know, I might get back into that. But if you do like $5, basically, you get to put credits in for the next game. So I had this guy's his name's like Dustin, and he's a patron, and he chose this TurboGrafx-16 game. So that's why I'm doing it, is because he wanted me to, basically. But it's based off like a bidding rank system. So the more money you put into the game, the higher up it goes on the list. So the one that has the most credits will be the next one that I corrupt. If that makes any sense. So, um, anyway, so we're scrolling down Kirby's Adventure, right? And eventually, about 2/3 of the way through, that's the tile data. So basically, whenever I'm corrupting a game, I will find stuff that looks like this, and I'll make a note of it. So it's like, okay, don't corrupt from offset 80 80010 all the way down to the end of the ROM. So don't even touch this. So my corruption range will be everything before that. Now, of course, you're going to have a game that is going to, like a Nintendo game that's going to use RAM um, for graphics, and that gets a little bit more complicated because then the graphical data could be anywhere, and it could be in multiple parts. And most games are like that are not Nintendo, because Nintendo's unique. It's the only system, I believe, that has a dedicated chip for character ROM. So, to give you an idea of that, let me think of one. You know what? This works because I believe The Legend of Zelda is character RAM, mainly because I believe it was kind of designed that way because it was originally a Famicom Disk System game. So, I think, actually, I guess they could have made it character ROM if possible. So one thing that I avoid is you see all this. This is obviously blank space. I mean, that's the header, duh, INES header. But all this is blank space. I avoid that. So I'm not going to corrupt there. There's no point if it's not being used. But, you kind of look through. You kind of see where everything is. You kind of look through here. Sometimes, if you can see here, it's not, aligned to the 16 bytes. Sometimes you have to hit plus or minus, and you can get it to where, it's in the right place. So I'm like, okay, I don't want to corrupt any of this. Don't want to corrupt that blank space. Don't want to corrupt this blank space. And then I kind of make these ranges of where I want to corrupt. I'm showing you this because we're going to get to Bonk's Revenge here. So let's open up a TurboGrafx-16 game now. So where are you? Here you are. So we'll do Bonk's Revenge. Now, TurboGrafx-16 uses something. It uses tiles that are much higher bit rate. That's why it's a little bit more colorful. You've got 16 colors to work with instead of just 4. Here's the problem with this, though. So this is Bonk's Revenge. So scrolling through. Do you see anything that, except for maybe here, do you see anything that looks like graphics? So you see some empty spaces, and we'll take care of that. How are you going to corrupt that? Oh, hey, Lucky Bacon as well. We're going to have to figure out where the graphics are, and that's what we're going to go over tonight, at least for a little bit. So I'm kind of showing you the problem of Bonk's Adventure, and this kind of applies to a lot of 16-bit consoles like the Super Nintendo, the Genesis. It's a pain in the ass, and I'm going to show you why. So there are areas of the ROM that are empty, so we'll skip over those. But we need to figure out where the tile data is, and as you can see, it's just a garbled mess. Again, except for some places here that could possibly be tile data, but it's all compressed. So when you don't have a dedicated character ROM like some Nintendo games have, that gives you the freedom to utilize compression to save on cartridge space. And it sucks because you can't clearly see it. Some Game Boy games can a little bit, and I've done that before, but here there really isn't any clear, defined place for character ROM. So, or rather, just tile data. I keep calling it character ROM because that's how it's called in the Nintendo Entertainment System. So, a lot of garbled blah 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 blah. So, how do you find compressed graphics in a game like this? And you have to go into the code and figure out how it works. And that can be hard. So let's go over something here. So the TurboGrafx-16 is not a popular console in the States. The Nintendo, very popular. So much, in fact, that if you were like, I want to play a Nintendo game, are there any emulators for it? Yeah, there's like I think about 100. I'm not kidding you. There are so many emulators for the Nintendo Entertainment System. Each of them has their pros and cons. Some are focused more on some things. Some are focused on other things. Some are more focused on speed. Some on accuracy. Some have good debugging. Some don't. Some are focused on tool-assisted speedruns, so on and so forth. There's even one that turns the game into and renders it in 3D. You've probably heard of that one. That one's pretty interesting to say the least. Now, so for something like, I don't know, Messin, you can see that this is something that has, well, we'll just pull up this, I guess, whatever. Anyways, one of my old corruptions. But if you look, you can see that, popular video game system is going to have an emulator out there somewhere that's going to have a robust debugger, and this is probably the best debugger that I've ever used. So, so it's great if you're working on a Nintendo game or Super Nintendo game. Like Messin S is the Super Nintendo version of that. Even Genesis, if you look around, you can find something with a relatively decent debugger. Even PlayStation, like I've heard DuckStation has gotten a better debugger. There are even forks that of PCSX that offer great debugging. One of which that I need to look at some point whenever I get back into hacking the BIOS, which is something I still want to do. I think I'll do that if I hit 4.5 thousand subscribers. So if you subscribe, then I can start hacking the PlayStation, and that'll be great because I'll probably share that with the RTC group. It's like, here's how you hack the BIOS so that the PlayStation doesn't crash so much. But it uses MIPS and it uses some weird stuff, and that's going to really test my debugging skills. It's going to be a rough ride, just based on how the MIPS works, if that makes any sense. So anyway, I have used the corrupt outrun. I don't know why. There's something about this that is. Can I put this back where I'm just gonna put this down here just for the time being, just because. I don't know why the top chat. Live chat. There we go. That should be better. Okay. So anyway, so Messin has, a robust debugger, and that's great. Let me turn that off. What does the TurboGrafx-16 have? In short, jack diddly fuck. The closest that I can think of that would have any sort of debugging capability, whatever, is the multi-emulator BizHawk. And the debugging features on this, relatively speaking, are limited. But let's load up Bonk's Revenge and see if there's anything that we can use to figure out where the graphics could be. And once we find the graphics, we might be able to set breakpoints and look at how the game decompresses, and maybe there's a point. If we find something like a pointer table, which is basically a table that points to all the compressed sections of of compressed graphical data, then if we're lucky, we can just use those. And then we may have to write something that goes through the whole thing because it really depends on how it's done. So yeah, so let's just go ahead and open up. Here we are. Oh, so yeah, I was dicking with that earlier, but Bonk's Revenge ROM PCE, that's fine. So this is how the game. I'm gonna turn that down so I can hear myself speak. Okay. So this is the game that we're going to be corrupting. Now, what do we have in our arsenal? Let's go over some of the let me pause this and let's go over some of the things that we have in our arsenal. So we can see that we have so this is the settings. That doesn't really help us much. I mean, we can turn backgrounds and objects off. I mean, that could be useful, I guess. But for what we're doing, we want to. I really got to stop forgetting switching. Yeah. I want to say Messin has a debugger that's like literally miles ahead of anything that FCE UX has to offer. It has like built-in commenting. You could look at events in real time. There's so much that you can do with Messin's debugger compared to FCE UX. It genuinely makes it look like nothing. I am not kidding. Um, yeah. So, would you imagine that you would corrupt Windows 7 on a VMware with the RTC file stub? You want my opinions on that? I wouldn't bother, honestly. So, or at least with how I corrupt things, I wouldn't bother. The x86 has so many protections in place that corrupting it is all you're really going to get are like random crashes and blue screens, hard locks, and things like that. I mean, if you want something visually appealing, you're going to want to target, the graphical services and drivers like with like the GDI and everything. But aside from that, you're more, unless you really know what you're doing, you're just going to be wasting your time. And I know that's not a request. I'm just letting you know there's much better things to do, really. If you want to find good corruption, much better things to do than to try to corrupt an OS. Also, you still got to be careful even within a VM anyway, because if you do something weird, the VM could. Well, I guess it's kind of safe in a VM, but I still wouldn't risk it. It's just not worth it just in general. Even if it was completely guaranteed everything stays within the VM, I still wouldn't do it. Because it's just crashy. But yeah. Anyway, I mean, it's a good question. It's just not something you'd want to do. So just various settings, that's fine, whatever. So this will help. So this is a background viewer. So if we frame advance here, well, background viewer should work, but it's not working for some stupid reason. What the hell's going on? There it goes. I think it's because of the refresh. So here you can kind of see what the background is doing. So it kind of scrolls through here in order to, it's basically a name table viewer. Same thing as like with the Nintendo. So we've got that. Not all that useful. Well, I think what we're more sound debugger can maybe help with vocal samples. We don't really need that, so we'll close that. File viewer is what we want. So when I first looked at this, I was a bit confused because, and I'm going to need to look this up a bit more, but apparently it has one for the background and one for the sprite. Now, these, even though they look different, this is showing the same memory space for both. But for some reason, I'm not too sure why, and again, this is something I'm going to have to look up. But apparently, graphics for the background is stored differently than backgrounds or sprite data. So tile data is different than background data. And as I said before, maybe let me take a look at something here really quick. Here we go. So I need to figure out how that works because yeah, that's how to write data. So the VRAM layout, I mean that kind of shows where everything should go. But apparently, pattern is 32 bytes in size, 4-bit planes, 8 lines. But it's different with sprites than it is with backgrounds, and I don't know why. Um, and it doesn't really tell me, which is annoying. Um, so it has tile definitions, but for some, okay. So tile definitions are different than sprite definitions. So so there's 16 by 16 4-bit planes, and so the way that they are stored is different for some reason. So that's why it looks different with these two in the tile viewer. So that is something that you have to keep in mind. Um, sorry, I'm not. Should also mention that lately I've been feeling a little bit sick. So what I may have to do is I might take a short intermission and then I'm gonna come back. But give me like 2 seconds. I'm just gonna let this play and I will be right back. Let me add a quick message here. Short intermission. Be right back. So just give me like 2 seconds, okay? Hold on 1 second. Okay, sorry about that. Hopefully it didn't take too long. All right, so who all's still with me? You know, it would be nice if OBS kind of gave me a bit of feedback on who all is still here. Hopefully you guys didn't leave, but if you did, I mean, this could be viewed later, so you know, it's not that big of a deal. All right, so we got the tile viewer, so that will help us see what's updated in real time. So that could help. Um, so that might be of use. Um, we have okay, so that's everything. You know, TurboGrafx-16, otherwise known as PC Engine or PCE in this case, in case you didn't know why that was called PCE. So we have tools. So toolbox, RAM watch, RAM search. For finding compressed graphics, none of those are going to be very useful. We don't need to do any Lua scripting. Now, hex editor, that can help. Um, that can be useful. Data size, we want that to be 1 byte. Memory domain, so this would be main memory. So that's going to be, I believe, just yeah. So that's just your RAM. So so that could be useful. Um, then you have the system bus, and these are essentially the what's currently stored in the which what sort of mappings is being shown. So that can be useful too. Um, and then something else that just dawned on me when it comes back to the whole tile molester thing. This um so it probably so Bonk's Revenge probably defaults to or tile molester probably defaults to one of the either the tile map or the sprite map modes for for how to put this. It either defaults to background or sprite because they're two different formats. So I'm not too sure which format I would need to set for one or the other. So that is something to keep in mind. But it's currently 4 bits per pixel planar composite. So it might be it could be this 4 bits per pixel planar. And that might show us something a bit different maybe. But because the more I think about it, the more I'm like, oh hey, you know, it could very well be that like for example, all this here, that might that actually looks like it's a bit clearer, so maybe maybe I'm onto something. But I don't know. As I mentioned before, this game's gonna be a bit difficult. But let's see if we can find some graphical data because I think once we find the graphical data, I think that'll help us. You know, so we have that tool. So there's also something called a trace logger. So this will, or am I thinking of? Oh no, that's code data logger. So if we were to run this, um, we we can see what the game is doing per frame, and if the game is loading graphics, we can get a general idea of where the decompression routine is, and that's important because then we can reverse engineer that routine, and and then there we can maybe figure out what the pointer tables are and everything else. So trace logger, it's going to be important. Now, um, next up is a code and data logger. This um, essentially keeps track of everything in the ROM and tells us if it's being executed as code, read, or written to. And that can be also very important. So, so once we're able to find essentially what's what, I mean that's one way of figuring out precisely where graphics data can be. So so that's also very important. And then, oh, I forgot one. So this will be important when we figure out where the decompression routine is, because then we can set a breakpoint and then kind of walk through the code. Uh, are the tiles even going to look that scrambled in a memory visualization? Huh. So I think what you're asking is, so another thing that we can try is taking a look at a RAM dump and seeing what's in there. So I think a lot of times games will decompress into a memory region. I know like Genesis games tend to do this a lot. I think some Game Boy games too, and it'll decompress into a memory region, and then it'll do some sort of DMA into VRAM. I was also looking at let's see how the DMA works, and from my understanding, the DMA is only for transferring sprite data from one area of VRAM to the other, like to update sprite positions and whatnot. Um, and honestly, I I don't know if there's any actual like DMA from like RAM to VRAM or DMA from ROM to VRAM. I wasn't able to find that. So all this is so with the graphics registers, all these registers deal with VRAM or I'm sorry DMA. But I didn't while looking through the documentation, it didn't seem like it was DMA from outside of VRAM. It seemed like it was all DMA from within VRAM, which didn't make sense to me. Yeah. So yeah, the conversion is done in RAM during the battle transition, and then pipe to VRAM. Yeah, that's what I thought. I really wish the chat here would not cut off like the last line of dialogue. Can I do this? Hey, there we go. That's better. Okay. I just had to pull it up a bit. Okay, so we'll worry about that later. What we want to do is see if we could find something. So this is what we're going to do. So I think step one is to reset. Don't save changes. I just had that open. And then what we're going to do is we are going to look at, where are you? Tools. So we're going to bring the tile viewer back up. So here we should be able to see, like if we do just frame advance, you can see that things are currently being written, at least to the background layer. So that looks like system font, and then it looks like the first thing that gets loaded is background data. So this here, that's background, that's background, that's background, that's background, that's background, that's background, that's background. Then I want to say that this thing up at the top. So if we go back to what the possible tile map stuff is, actually, interestingly enough, so minimum tile map. Yeah, I don't know where yeah, it's kind of different. Never mind. I think they might have some things wrong. So you have the tile map, and then I think before that you have like the name table type data. Oh, actually, you know what? They're calling it, okay. So no, you know what? I take that back. So they call the tile map the name table data. So and then they call tiles. For some reason I was getting my terms reversed. So yeah, so now it loads the tiles, then it loads the map, and then I think it loads. Here we are. Then it loads. Here it is. Let me get rid of this really quick. Close that out, and then here we go. And then so up here, that's your tile map. So and then it loads the sprites. So here's the sprites being loaded. So everything that's kind of a yellowish color. Interestingly enough, they've only got 1 or 2 pallets loaded, and that's bonk, obviously, so it loads bonk pretty quickly, which makes me think that maybe bonk is uncompressed. If that's the case, I got to figure out how to get that showing up in Tile Molester here, because if we can get that loaded up in Tile Molester, because it loads the sprites a lot faster. I'm not too sure why. So we can see that it takes several frames to do that. So what we're going to do is I want to figure out where the background tiles are loaded first. Then we'll worry about sprites. So we're going to do this. We're going to reset. Okay. Now we're going to skip ahead maybe a couple frames here, like that. Now, and maybe do one more, maybe 2. Okay. So we're saying that it's starting to write on there. Now with the tools that we have, the best let's actually do a couple of things. So there's 2 ways to approach this. One, we could data log it and figure out where the data is being read on the ROM, and that will give us an idea of where this data is. Alternatively, we could also do logging, and it'll show us what's currently being executed. And we know right now that it's running through some sort of routine, some sort of decompression routine, putting everything into the into VRAM. So sorry, like I said, I over the past week I haven't been feeling well, so if I look a little uncomfortable, that's why. So I'm trying to think the best way to do this. I think it would be quicker to do it the way that I'm thinking. We could also see really quick if we go into the debugger. So here's how everything is. So here are the banks that it currently has selected. So sorry. So basically, so this is going to be your bank that deals with the GPU registers and sound registers, all that fun stuff. And then next up would be, this would be your RAM. So your RAM is going to be in NPR1. And the rest are mapped to ROM. So 2, 3, 4, 5, 6, and 7. So 7 is apparently always going to be mapped to the first bank in the ROM, because that's where your that's where your interrupt vectors and everything are. So that's kind of important that has to be there. So that's always going to be 0. But let's see here. If you're trying to follow the lead from the VRAM back to the program in order to figure out the ranges for the compressed tile assets in order to leave them untouched. Yes, that's kind of where I'm going with this. So I may have to step out for another few minutes again here in a bit. Again, like I said, I'm not feeling well. If you see me like sweating, that's why. So what we're gonna have to do is I'm debating on logging, or because with logging we'll see the exact location in the ROM, but with this we have to make sure that the registers are in the right place. Actually, give me like another like 5 or so minutes. It's for intermission 2. So give me like 2 to 5 minutes here. Again, my apologies for the second interruption. So, thought over. I think we're going to tackle it this way. We're going to run a logger for one frame and see what code is executing. I think once we figure out what code is executing, we can like set things like breakpoints, and then from there, we can also see what mapper registers are being set, what address is being accessed, and that will give us an idea of where it's actually pulling that. Um, he released the RTC. I mean, congratulations. For those that are unaware, I use my own methods. My methods predate RTC, and while it's a great tool for people that want to corrupt their own media, um, it's I have a different philosophy. So, um, but I mean that's great. Actually, Lazar, if that's how you say that, he actually implemented my exception handler for the Genesis as like a blast layer in the whatchamacallit, in the corruption research channel if you want to check that out. That should make Genesis corruptions a lot easier, hopefully. Should. I spent, I'll make a quick side note about that. I spent, I think, a good week or so, I think, like going through each and every exception to and figure out the behavior to make sure that it would work perfectly. And so it was a bit of assembly code, you know, but but I was actually able to pull it off, and when I tested it worked very well. And that's what I use for BattleTech, Echo the Dolphin, and the third volume of Sonic 3. And if you look at my third Sonic 3 corruption, it's really good. I also used it for Sonic 3D Blast. That's why you don't see the level select menu when I corrupt that game, because I wrote something entirely different for it. So that's whoa, okay. So we have a time limit now, so we're only going to be doing this for another 20 minutes because someone decided to book a class with me. So I teach English, so and I have my schedule, available at any time. So sometimes someone will just pop in and do this. So let's see how far we can get. And see if we at least get something. So what we're going to do is this. Where's my trace logger? It's this one, right? So I think we're going to lock the file, and it'll be under BizHawk Tools, Bonks, Revenge. Okay, that's fine. So file. So we'll start logging. Okay. Now we'll run it for one frame, and we'll stop logging. Now we'll open it, and as you can see, this is essentially a disassembly of basically this is everything that ran during that frame. And you can kind of see that it's going through a loop, basically. So this is quite a lot to go through, but this at least gives us an idea of what it's doing. So I don't know if you've ever looked at a trace log before, but let's see here. Hold on. Open the SpongeBob is watching. Okay, it's basically the equivalent of IPS patches, but in real time, frame in memory. Oh, that's cool. Yeah, yeah. I'm just kind of looking at this exchange here. Yeah. Yeah, if this was something that was focusing on RTC, or something like that, then that would be relevant. But this is mainly focusing on reverse engineering a TurboGrafx-16 game for my own video, and I don't use RTC. Again, not to discredit RTC or anything. It's wonderfully engineered piece of software, but this is just going over just kind of figuring out where stuff is in a game, so that if you don't want to corrupt it, you don't have to. So it's delving in a little bit deeper. So, but let's go over how to read something like this really quick. So we'll just scroll back over to the top. And again, like I said, I'm only going to do this for another 10 minutes or so because I got to hop onto a class. But we're going to look this over and get a general idea. So this is I think so this processor is an 8-bit CPU. This is always going to be 0. Okay, so we don't need that. Don't worry about this first part. This is the 8-bit address. So given the fact that this starts with F, this is using like that last bank. So you kind of have to do a little bit of math here. So MPR 0 is going to be 0 0 0 0 to like 1 FFF. This is going to be 2000 to 3 FFF, 4000 to 5 FFF, etc. So this is going to be let me think here. E000 to FFFF. So, what does that mean? Well, you have to do a little bit of hex math in your head, but basically, it's executing in this region, which makes sense. It's the first bank of ROM, and that's always going to be 0. So if I was the developer, my guess is that all of the system critical game engine code is stored in the first bank of ROM. Okay? Because you need it for bank switching, for decompression, for all these other things. You could probably have code in other banks, but the meat and potatoes is going to be in that last bank. So we're actually right here. So you can kind of get an idea of where this compression routine is. With that said, now you just kind of have to look at a few things here and kind of figure out what's going on. So this is going to be your 8-bit address, and that's going to map to usually a place in ROM. Here it's going to be the first bank. Okay. So it's probably going to be address 11D7, right? There's one way to check for this and make sure you're correct is if you go into the hex editor and go into the memory domain system bus. That should be a ROM, okay? And we scroll down to what was it? 11D7. So 11D7. I cannot. Okay, so see how that says 8D? 8D. Okay, and this is a store to store whatever's in the accumulator into this address here. Okay, so you can see now. Remember, Motorola processors store everything in Little Endian. So this is least significant, most significant. So it's 0002. So, which is a register. Interestingly enough, so I think it's actually writing to VRAM. So this here is writing to VRAM, which is weird because if I recall correctly, the Hudson Soft processor has a special instruction that does this exact same thing. So I don't know why they're doing it this way. I never really understood that. But in all fairness, I'm not that familiar with this architecture. It's brand new to me, so I'll probably look at it later and be like, oh, duh, that's why. But so okay, so you've got this. So that's obviously 1D7. So we know that's somewhere in the in the stat in the so that's somewhere in the routine. We'll figure out where the routine is later, but that's a good start. We figured out where the compression routine, decompression routine is, so that's good. So next up, this is the instruction that it's reading. So store accumulator. One of the store accumulator registers is, or not registers, but instructions is 8D. This is the instruction itself. This is telling you what exactly it's doing at that moment. Now it's telling you everything that's in the registers. So this is your standard 6502 stuff. You got the accumulator, which is storing into 00002. You've got two index registers, X and Y. These handle things like looping and address offsets, that sort of thing. Very important things when you're processing stuff. So the next ones are a bit crazier. So I want to say I don't know what P is. P I'm gonna have to look up. That sounds kind of dirty. I have to look up some P. This is probably going to be your stack pointer. So actually no, that's not it either. Okay, so stack pointer. So this kind of tells you. So you have to keep. So for 8-bit CPUs and a lot of other CPUs, you have to, because of how limited the registers are, you usually have to push and pull things from the stack. I mean, I guess that goes with any processor, but it's even more important when you have a processor that's so constrained. Like modern processors have 16, 32 different registers, sometimes more, depending on how modern the processor is. You can see that there's only a small handful of registers for 6502 based systems, which makes it kind of easy to keep track in some ways, because I only have to deal with like three main ones here: A, X, and Y. But you also have to keep track of the stack pointer. I think this is cycles. So we don't have to worry about cycles, I don't think, because we're not worried about timing. We're just worried about what it's doing. If we're worried about timing, then cycles would play a factor here. And then this is a representation of the excuse me, of the status flags. So basically, status flags are used for determination, like in conditions. So if you're running some sort of algorithm and you want to go somewhere else, if the result is 0 or less than 1, so it's like, hey, if this value is 0, do this. It reads these flags to determine if it needs to do one thing or the other. That's how basic processors do that. So you kind of have to look at that to kind of figure out what it's doing. Are we on time? 7:21. Okay. So where do we go from here? That's a good question. What we would want to do is we would want to make some notes. So here's what we know so far. So we want to kind of keep track of these things. So decompression routine is around 0x. So that would be what, 11D7? I think so. Like that. So that's where we know where it kind of is. We'll have to keep looking through this and have a kind of a better idea of, actually, we could probably say F1D5, because I'm kind of looking through these addresses here. It's like, what's the lowest address that we can find? So obviously it's looping because you see the same addresses over and over and over again. So it's processing data. What data is it processing? If I had to guess, this is LDA, and it says the indirect address is 03. So whatever 16-bit address is at 03, that's probably where it's reading from, if that makes any sense. So if you look, so it might just be loading uncompressed data, which means that Tile Molester's got it wrong. I'm gonna have to look into it more. But yeah, what pumpkin? Okay, you know what? Nope, 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 nope. You're gonna bug me. You're gonna go on camera. Cat cameo time. So we're gonna look and see what indirect address is for 03, and then we're gonna wrap it up. And the next time we'll try to figure out where it's pulling all this data. So how does oh way different than the Z80. The Z80 is a completely different architecture. I think the 5822 is the NES CPU, right? I think, or it's one of them. I'd have to look it up, but if it is what I think it is, it's very similar, a little bit more advanced. Oh, oh, the SNES one, the 65CA60. It's a lot closer to the 6502 than the 65CA16. A lot closer to the 6502 because it's completely 8-bit. Like these registers are essentially 8-bit registers. So I'm going to be really quick about this because I'm really running out of time. But so fuck, where is it? Hex editor. So if we go into memory domains, main memory. So 3. So it's probably pulling from 3902. So 2 to 3, which honestly wouldn't make much sense. It might be pulling from RAM, I think, because it's yeah, I think it has to be pulling from RAM because RAM is in the second bank, logically speaking, and 3902 would be in the second bank. So it's probably decompressing to RAM, then pulling from RAM, and we'll have to take a closer look at that. So that will help. So I might do another one of these tomorrow. I don't know yet, but I've got to get ready for a new class. It just popped up, so but that tells us a bit. That tells us that it's probably decompressing to RAM and then from RAM to VRAM. So that would make sense. So we'll have to look into that. We'll have to look and see how that works. But with that said, I got to get going. So because it's like 3 minutes left. So I wonder who pulled this class. But yeah, pretty exciting stuff. Pretty exciting progress. But next time will be even more interesting because we'll really start to get into how this works. So, but I gotta stop. So great having you guys. Thanks for stopping by, and I hope to see you for the next one. Bye for now.